Welcome back to Math 104. If a weather forecast says that there is a 30% chance of rain on Saturday, a 50% chance of rain on Sunday, and a 60% chance of rain on at least one of these 2 days, then what is the probability that it rains both days? Let's first define events E, that it rains on Saturday, and F, that it rains on Sunday. What information is given, it's a good idea to write this down clearly. It is given information that probability of E equals 0.3, probability of F equals 0.5, and, this is the kicker, probability of E union F equals 0.6. This is crucial. We need to be able to interpret the language here and see that the event that it rains at least one of these 2 days is precisely the event E union F, that it rains on Saturday, or that it rains on Sunday, or that it rains both days. That's another way of saying that it rains on at least one of these 2 days. We are asked to find the probability that it rains on both days, which is the event E intersect F. And isn't it great that we have an equation that relates the quantities we know to the one that we are trying to solve for? We substitute in the values that we know and we solve. So 0.6 equals 0.3 plus 0.5 minus the probability that we're looking for, that of the intersection. 0.6 equals 0.8 minus the probability of the intersection. You can stare at this and say, it must be that the probability of the intersection equals 0.2. Just to be spectacularly thorough, I'm going to add probability of E intersect F to both sides, and then I'm going to subtract the 0.6 from both sides to discover that the probability that it rains on both Saturday and Sunday equals 0.2. Having solved this problem, let's now interpret it in terms of a Venn diagram. By interpret the results in terms of a Venn diagram, I mean write in each basic region the probability associated with that region. Along here are written all the probabilities that we've thought about thus far in this problem, and we start by asking, of the probabilities we know, which, if any, is the probability of a single basic region? There are 4 basic regions in this diagram, and of these probabilities, only the last one, only the probability of the intersection, is the probability of a single basic region. And therefore we write 0.2 into that region, and we proceed by working outward from there. Thus the probability of rain on Saturday, but not Sunday, inside the E circle but outside the F circle, is not 0.3, but rather 0.1. 0.3 is the overall probability of rain on Saturday, represented by the entire E circle, both regions of it. So the total probability of E adds up to 3 across those 2 regions. Similarly, we write 0.3 here in the region inside the F circle but outside the E circle. Where did 0.3 come from? It's 0.5, the probability of F, minus the 0.2 that's already been accounted for in the intersection. The probability of F overall equals 0.5, and that 0.5 is the sum over both of these regions that belong to F. Now notice how these 3 regions into which we've written their associated probabilities all contribute to E union F, and nothing else is part of E union F, and sure enough, the sum of these 3 probabilities across these 3 regions is indeed 0.6, the probability of E union F. Finally, we must not forget the outermost region, outside both circles, the event that there is no rain either day. Since all the probabilities in the experiment must sum to 1, and 0.6 of the total probability has already been accounted for, that leaves 1 minus 0.6, which is 0.4. 0.4 is the probability of no rain either day. Now we are ready for the third of our operations on events, the complement. The complement of an event E is the event denoted in this way, E with a line over it, and read E complement, which consists of those outcomes that are not in E. E complement is the event that E does not happen. Please note that the word complement is spelled with an E here, not an I. As an example, recall the event L, there is at least one girl, in our experiment of randomly selecting a family with 3 children and observing the birth order of boys and girls. We can ask, what are all the outcomes in L complement, and what is its probability? The event L complement is the event that this does not happen, that L does not happen, that there's not at least one girl. So there is only one outcome in L complement. L complement therefore has probability 1 out of 8. There is a 1/8 chance that L does not occur. We can draw a shaded Venn diagram to represent L complement. In order to do so, we're going to have to shade everywhere outside the circle L, and that means truly everywhere outside it, including inside the F circle, but outside the L circle. So everything outside the L circle is being shaded here. Think of it this way: the event L complement makes no mention of F. So when we do the shading for L complement, we proceed as if the F circle were not even there at all. We shade everything outside of L. It makes sense if you think about it, that for any event E in any experiment, E union its complement equals everything, equals the entire sample space. That is to say that every outcome in the experiment lives in E or in E complement. We don't even need to say or both, because nothing can live in both E and its complement. We say that E and E complement are complementary events. So for example, there is at least one girl and there are no girls are complementary events. Either this happens or the other one happens. Not both, but one of them has to occur. What does the addition rule have to say about this? The addition rule says that the probability of the union of E and E complement, which we've just figured out, is the same thing as the probability of the entire sample space, which has to be 1. That equals, according to the addition rule, the probability of E plus the probability of E complement minus the probability of their intersection. But wait a minute, what is E intersect E complement? It is exactly the null set that we talked about, the null event, the empty event, the event that has no outcomes in it. It is impossible for an outcome to be in E and in not E. This is why we had to define such a crazy thing as the null event, and its probability is 0. There are no outcomes there to contribute anything to its likelihood. What does this all boil down to? 1 equals the probability of E plus the probability of E complements, and there is nothing to subtract off. Aha, that's going to be a useful formula. Let's even give it a name. This is the complement rule. The probability of E complement, that is the probability that E does not occur, is 1 minus the probability of E. To sum up what we've done so far, E union F is the event that E or F or both occur. E intersect F is the event that E and F occur. E complement is the event that E does not occur. The probability of the union of E and F equals the probability of E plus the probability of F minus the probability of their intersection. That's the addition rule. And the probability of E complement equals 1 minus the probability of E. This is the complement rule.